Good afternoon, everyone. Thanks for being present this appointment in the Science Colloquium. And today is our pleasure to host Professor Jordi José from Department of Physics, University of Catalonia. Jordi is a full professor of physics, and also head of astronomy and astrophysics group. And as today I told to the students of the course of astrophysics, Jordi is worldwide recognized scientist in the field of explosive nucleosynthesis, and it's a friend of us. And with him, we have the pleasure to share moments in which we do research. We do research in a friendly atmosphere. So it's a great pleasure for us. And please go ahead. We will have first part for the talk, and then I will encourage students to ask something to our speaker. Okay.
Thank you very much, Livio. It's always a pleasure to be back in Catania. I've been many times, and I never get tired. And I'm happy to see that aside from familiar faces, to see also some young faces, okay, which is also a good sign for the field itself, okay? We need young people to bring new ideas and new, enthusiasm to the field. So again, after thanking Livio and Gianluca and the rest of the department for this kind invitation, if you are ready, we are going to start with this journey through several of my favorite stellar explosions, okay? So I know that we have here a blend of people, some experts, others that are not so much experts or, knowledgeable of the field. So I started with something that may resonate in your brains. Maybe you have seen something like that before, which is more or less like the big picture of what to expect in terms of the evolution of stars, okay? So probably everybody here is familiar with the idea that the stars are like humans, essentially. So they are born, they evolve, and at some point they die, okay? However, when they die, they form, instead of just a corpse, like what we usually do, they form a stellar corpse. And stellar corpses have, differences, okay? So they are usually quite compact. So when you have a star that initially has something like up to 10, roughly speaking, 10 solar masses, I mean, I have only 45 minutes. I can spend 45 minutes with this slide. So I have to skip some details, right? So, I mean, I will make like some general statements. I know that because some expert will say, well, it's not 10, it's 9.2. Okay, fine. But again, to simplify, let's fix like around 10, okay? Below 10 solar masses, 10 times the mass of our sun, stars experience more or less a smooth life and end their lives basically as a compact object that we call a white dwarf, okay? White dwarfs have a maximum amount of mass of about 1.4 solar masses. This is what we call the Chandrasekhar limit. And to give you an idea, we have encapsulated the mass of an entire star in an object that has the size of a planet. Okay, so we are talking about several thousand kilometers, much smaller than the size of our sun. So you can figure out in your heads what is the typical density of a white dwarf. That's nothing compared with the fate of a more massive stars above 10 solar masses that experience some sort of a more explosive events, supernova explosions, and then end their lives in the form of a neutron star or a black hole. For this talk, I'm just going to talk about what to do with white dwarfs and neutron stars. Okay, we'll skip black holes. And just let me remind you that a neutron star can have a maximum mass of about 2 to 3 times the mass of our sun. But instead of talking about putting it inside an object that has the size of our planet, this is basically the size of Catania, okay, or a little bit more. Okay, so 10 kilometers. So imagine the density at the center. We are talking about 1 cubic centimeter of material from the center of a neutron star weighing something like, I don't know, 10 to the 15 grams, something like that. So incredible densities, okay? Well, That's it. So you may think, okay, if this is the final fate of any star, that's it. I mean, let's finish the colloquium here, the shortest ever, right? And we can go home and enjoy the rest of the day. It's a sunny day. Well, not really, because that's not the end of the story. That's the canonical picture in the evolution of single stars. But it's important to realize that about 50% of the stars in our galaxy are not single, okay? And you know that life, when you have a partner, it's funnier. Okay, I'm not entering into this area because that could be offensive to some people. But there are episodes in which these two objects can even transfer material from one to the other. Okay, and that's a way in which some of these systems, with all the multiple connections, the movies look like a little bit crazy. Okay, usually you will see them in a much smoother way. But there are multiple connections to make this, to record the session and everything. But basically, there is a significant fraction. I said 50% of the stars in our galaxy form double or multiple systems, and a fraction of them contain already one of those compact objects, a white dwarf or a neutron star. And that's the way in which nature found an alternative path to revitalize these otherwise stellar corpses and bring them back to life in an explosive way, by the way. Okay, so basically, we know systems, we observe, and we know that there are some of these systems that are close enough that allow basically the strong gravitational pull exerted by the compact object to strip the outer layers of the companion star, transfer material, accumulate on top of these compact objects, and then undergo some sort of destabilization and a further explosion. Basically, this is the mechanism that gives rise to some of the phenomena that you may have heard before. When you have a white dwarf hosting these mass transfer episodes, you can have Type 1a supernova explosion or a classical nova explosion. Okay, we are going to talk about them today. And then if I have time, I will tell you a few lines at least of what happens when you have a neutron star hosting the mass transfer episodes. And this gives rise to something called X-ray bursts. Good, but not only, okay, because there are multiple other phenomena. These are the most famous probably, but there are all other phenomena. Probably you have heard about stellar mergers, okay? There are situations in which you have two of these compact objects in the same binary system that can undergo, by emission of gravitational waves, they get closer, 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 and then at some point, essentially they merge. That's the case of two white dwarfs. These are simulations done in my group in Barcelona, where essentially this is one of the mechanisms that have been suggested to give rise to a supernova explosion. Okay, probably you have heard more in recent times that when you have two neutron stars, they can also merge and give rise to a phenomenon that is called a kilonova explosion. Okay, and we have observed that indirectly through the detection of gravitational waves from the merger. Okay, good. So there are different phenomena, and just to raise your interest on that, there are situations in which you can have a white dwarf that collides with another star. Okay, there are environments in our galaxy that are essentially very stellar rich. Okay, the density of stars there is large, and then you can have even head-on collisions, like we explore in that paper, or in the next one, of center collisions between a white dwarf and a normal star. Okay, and I just raised this issue. This was published in February this year. Okay, because this is a scenario that allows us, for those that work in stellar nucleosynthesis, in the creation of the elements, to identify which elements are produced in these violent collisions between a white dwarf and a main sequence star. And just let me emphasize that one of the findings that we obtained here was that beryllium-7, that later will be transformed into lithium-7, is one of the outputs of these scenarios. So surprisingly, or not, wherever you have a star that is rich in hydrogen and is exposed through an event, a collision, a merger, or an explosion to high temperatures, this essentially invokes some lithium production. So my take on that, we don't know, is one of these elements that we don't know really where it is produced. My take on that is that lithium is produced in multiple different scenarios, and different proportions essentially build up the amount of lithium that we observe in the galaxy today. Well, let's start with some of the typical mechanisms that I mentioned. One of my favorite are supernova explosions. They come in different flavors, essentially, okay? You have here some, okay? These are, by the way, these are what we can call them type 1, or if you prefer, type wine, okay? These are very popular in Catania, by the way, from previous experience. But of course, there is always that preferred type 2. Course. So these are the other type of supernova explosions, okay? So back to the title of my talk, these are the objects that make Kaboom, the most, violent event in terms of the family of stellar explosions that we are familiar with. Let me mention that at least we can classify them in two big groups: thermonuclear supernovae, that correspond to those white dwarfs revitalized through mass transfer from the companion. Again, novelties, as soon as we dig a little bit more and we extend our sample of observed supernovae. If you look at any textbook on astrophysics that deals with the stellar evolution, the typical message that you will find is that the white dwarf never survives the explosion in a type 1a supernova. It's fully disrupted, okay? And that's essentially the little pieces smashed of the original object are scattered through the cosmos. Except that more recently, there is a subtype of type 1As that are called type 1AX, okay? That accounts already for 30 objects, so it's not just one or two, so we know at least 30, in which there is evidence of at least a partial survival of the original white dwarf in there. Okay, so that opens the door for multi-D effects, the idea that some asymmetric explosion, maybe a highly rotating object, something makes some difference. In most of the cases, the star gets fully disrupted, but in some cases, at least part of the original white dwarf survives this strong phenomenon. Okay? Good, and then there is a second, under the same umbrella of supernova, second type of objects that essentially involves massive stars, about 10 solar masses at the beginning, that end their life in a very unstable situation and gives rise to the formation of a neutron star or a black hole, accompanying with a phenomenon that resembles a thermonuclear supernovae, even though this is not really an explosion, it's more driven by the collapse of the central regions, and we call this a core collapse supernovae, okay? Wow, these are amazing things. And actually, you may wonder, okay, but wait a second, we live in the Milky Way. In the Milky Way, we have white dwarfs, we have massive stars. So is it possible to have a galactic supernova like that and observe that, how bright this event is going to be? Well, the answer is yes, okay? In fact, we expect that in a galaxy like ours, we expect a supernova explosion every 30 to 50 years in average, okay? But again, remember that statistics is a tricky area, okay? Statistics tells you that, for instance, if you have a rich neighbor that has 10 Porsche cars, okay, and you have 0, in average, each of you have 5. Okay? But again, the reality is a little bit different. That's what the statistics say, right? But the reality is a little bit different. So let's have a look at the statistics here. Okay, so this is the list of all the supernovae that have been, that from which we have evidence that have been witnessed, observed, to explode in our galaxy. Okay, hopefully at some point there were people that liked to record whatever was happening in the sky, in the heavens. Okay, and then leave to the humankind a record of these observations. Okay, there are some very exciting things. Again, I can spend an hour talking on that. There is this object. It is called the crab with a B. Okay, Crab Nebula. Okay, and you may think, okay, fine, because they are constellations, right? And Crab is one of the constellations. Yeah, but not. That would be too simple, okay? This is actually in the Taurus constellation. And then you may think, okay, wait a second, I'm confused. What the hell somebody decided to call this Crab with a B, okay? If this is in Taurus, not in Crab, okay? Well, welcome to astrophysics, okay, where not everything is as evident as it may look like. The idea is that somebody, when actually looked at the remnant of the explosion for the first time, apparently saw the shape of a crab, okay? And even the object is in Taurus, they call it crab because of the shape of the nebula, Okay, but again, that could be confusing. And that was recorded in the 11th century, thanks to our Chinese colleagues. Okay, they had, imperial astronomers, astrologers, probably at the epoch, that recorded all these observations. And thanks to that, we can witness now what is the appearance of a star that has exploded after 1,000 years. Okay, so you have two options. You wait 1,000 years. Okay, technical problems involved, or then you look at some of these objects from which we know more or less when they exploded. Okay, and now in a beautiful example of cosmic conspiracy, what happened was the following: in just a 30-year period gap, there were two supernova explosions in our galaxy. To give you a flavor, just with the light emitted by a galactic supernova, you can read by night. Okay, so this is the second most, brightest object in the sky after the full moon. Okay, and Tycho, famous astronomer, and then later Kepler were gifted with a galactic supernova exploded at their epoch, and because they were the best astronomers of the epoch, probably they let us some sort of a very a diary with the details of those explosions, as we will see. But now, if you have some knowledge about history, you will recall that Galileo was the first guy that used a telescope. And that was basically by 1620, something like that. So now the funny part, right? So supernova should explode every 30 to 50 years in our galaxy. But since 1604, zero. Okay, and funny enough, after Kepler, Galileo came with the better instruments to observe those supernovae. Now we have everything. We have ground-based telescope. We have space-borne observatories. We have detectors of gravitational waves. We have everything, right? But no supernova. Okay, so this is one of the things that I can at least say in public that I would like to see before I die, a galactic supernova. Okay, now we have discovered the evidence of some supernova that exploded in our galaxy, even though we have not witnessed them. What we call a posthumously discovered supernova. Okay, one is the famous Cassiopeia A, that just by measuring the velocities of the remnant, we can infer more or less at which epoch on Earth the object was basically observed in outbursts, or potentially observable in outbursts. Okay, and that was in the 17th century. But again, remember, our galaxy is basically flat. Our probability or possibility of observing everything that happens in our galaxy is not the best. Okay, and so probably the object simply was not visible from Earth at that time. Okay, and the same applies to this one, whose name is a little bit more complicated to remember than Cassiopeia. Okay, that was probably observable in principle from Earth in 1868. Okay, so a few things about Type 1a supernovae. Well, this is a nice image of what to expect. Okay, so they experience an incredible rise in brightness. So how bright? Intrinsically, an object that experiences a supernova explosion reaches something like 10 to the 10 times the brightness of our sun at peak. Okay, so an incredibly bright object. Okay, and if you saw some of these previous slides here, this is one object exploding as a supernova, a Type 1a in fact, and this is the galaxy in which the object was exploding. So one star rivals in brightness with the light emitted by 100 billion stars in the same system. Okay, so that gives you a flavor about the pyrotechnics involved here. So how much energy is released during the explosion and how bright the event is going to be. Okay, so I was mentioning this one. So basically, to give you a flavor, the maximum brightness is a measure, basically, of the amount of nickel-56 that is produced in the explosion. Okay, and then basically the decline depends on is again another nuclear physics exercise. Okay, the early decline, steeper, is basically powered by the decay of nickel-56 into cobalt-56 that occurs in a relatively short time scale. The half-life of nickel is 6 days. And then once nickel is gone, then cobalt decay starts to play a relevant role, and that's responsible for this change in shape. okay? Because this occurs in a typical half-life of 77 days, the decay of cobalt into the stable iron 56, okay? So one of the main take-home messages from a type 1a supernova is that they are incredibly important. They are the main factories of iron in the universe, okay? More than actually core collapse supernovae. Now, if you want to be amazed, I mean, always are when I show this picture. What we have here are some dots and a solid line, right? The solid line is essentially the average of multiple supernova explosions we detect in other galaxies. They are so bright that on a daily basis, we detect 1, 2, 3 supernova explosions in other galaxies, okay? So we have thousands of records of supernova explosions that have been basically analyzed. And so this is basically the template of all these supernova explosions. What are the dots in there? Well, this is a reconstruction of the diary of Kepler, okay? 17th century, when Kepler was witnessing the galactic supernova, the famous Kepler, he took some notes and actually was following how bright the object was. But careful, without telescope. He was doing that with his eye, right? Naked eye observations, okay? And then you can see how the values that Kepler provided compare with the template of the type 1a supernova explosion, okay? That's what I would call a skill observer, okay? A skill observer. I mean, probably my data points will be here, there, okay? Anyway, good. Now, you may think, yeah, but all this is theoretical. How do we know that this is cobalt involved? Two answers to that question. For the first time in 2014, we detected gamma rays emitted from one of these relatively close enough, not galactic, but relatively close enough supernova that have been observed. And as you can see, the way I identify, well, I don't know whether you can read that for the very end, but basically we obtain confirmation of the discovery of certain lines associated with nickel 56 and cobalt 56. So that's the first unambiguous evidence of the main mechanism that powers a type 1a supernova, thanks to gamma ray astronomy. Okay? That way, there are other mechanisms that I'm going to tell you. But before everybody leaves the room thinking, oh, we know everything about type 1as, let me tell you that even type 1a supernova are being used today for cosmological applications. Probably you have heard about dark energy, okay? Dark energy is a concept that for the first time was guessed by observing distant supernovae. So by analyzing the properties of distant stars that explode as type 1a supernova, we can infer properties of the geometry of the space-time, of the universe itself, okay? Even this is the context, there are still things that we don't know about type 1a supernova. For instance, we don't know exactly the nature of the system that undergoes a supernova explosion. We know, or at least we are very confident, there is a white dwarf that explodes, but we don't know whether the companion star that transfers material onto the white dwarf is a second white dwarf, an experienced emerge, or is a normal main sequence star like the sun, essentially. We don't know that. Okay, so this is like a big question mark. We don't know exactly which systems actually end up as type 1a supernovae. We also don't know once ignition occurs, and models suggest, I mean, we rely extensively on numerical simulations to, improve our knowledge on these explosions, simply and hopefully, actually luckily, because otherwise some countries, and I'm not going to name anyone, would test that at home. Right? So let's do a supernova in the garden and see what happens, right? Well, hopefully we cannot do that, okay? And again, everything relies on numerical simulation, okay? We know that basically the explosion occurs near the center simply because, well, put yourself in a metro, in a big city at rush hour, okay? If you're at the center of a coach, well, you will collapse there, okay? So the temperature becomes really high, okay? And then that's where basically we believe that the explosion, according to models, begins, near the center. And then how fast this propagates? Another big question mark. We don't know, okay? You may have two possibilities. It may propagate supersonically. That's what we call a detonation, okay? Or it may propagate subsonically, so at a velocity smaller than the speed of sound. Okay? And this has different imprints that we can compare with observables to infer the lack of knowledge on the properties of how fast this burning front propagates, okay? And I put here some examples. These are simulations, multi-D simulations of what happens, what would be the result of a white dwarf that would experience a supersonic detonation or a subsonic one. And you can see this is a color code that indicates what is left over after the explosion, okay? Which material appear at different depths. Okay, this is the center of the white dwarf, and here you can see a striking difference. In these models below, everything is red, okay, and this is nickel 56. Okay, so the conclusion of the lower models is that at the center of the white dwarf, everything is essentially incinerated into nickel 56, whereas above, that's not the case. You can see a lot of unburned carbon and oxygen there. Okay, and then surrounding that blobs of nickel 56. Which of the two different results is correct? Well, we can take spectra, analyze the light coming from those objects, and recall we are talking at a very compact object, meaning that at the beginning, this object will start to expand, actually very fast, at typical velocities of the order of 10,000 kilometers per second. And so essentially, you will manage to see some sort of a tomography. You will see deeper and deeper layers as time goes on, okay? Basically, this is what you see 1 week after the explosion. Just look at the upper line. These are other types of supernova explosions. And this is what happens 5 months after the explosion, later on, okay? Early, what we see is just the outer layers, the ones that become transparent and then allow photons to escape that plasma earlier, okay? And what we see is basically a blend of material. We see iron, but calcium, silicon, oxygen, magnesium, so intermediate mass elements. And this is in agreement with basically all the plots that we have here. Outside, we don't have essentially just a red layer, okay? Which means that we have unburned material in the outer layers, okay? But as soon as time goes on, what we only see is that deeper in the star, we only see iron, basically, and cobalt. Okay, so these are the products of the disintegration of nickel 56. Okay, so which means that from these two options, these two are the favorite ones. This doesn't reproduce the observations. Okay, and that's again the importance of this multi-discipline treatment in nuclear astrophysics, combining observables, so observational astronomy, computational astrophysics, nuclear physics inputs to be able to have good nuclear reaction rates to make predictions in terms of which elements are going to be produced, okay? It's the magic blend of these different components that makes nuclear astrophysics so interesting and actually so successful. Okay, good. Let's move to novae, okay? So these do not make kaboom. These just make bang. Okay? They are much more modest, as the name indicates. Supernovae, it has to be something spectacular. Novae are much more modest. Okay? And since I'm considered myself a modest person, usually I work more on novae than on type 1a supernovae, but that's a different stuff. Okay? Well, again, one slide in which I can spend my life talking about. Basically, the important message here is, again, these nova explosions occur in binary systems, okay? And basically, it's a white dwarf that hosts the explosion, okay? Often from a normal star, but sometimes it's a red giant companion that we have transferring material into the white dwarf, okay? Now, the important difference between nova and a supernova explosion is that in 99.9% of the cases, the white dwarf gets disrupted in a supernova explosion. That means that objects that undergo a supernova explosion most likely undergo a single explosion, because the star is gone. For novae, that's not the case. Essentially, is the amount of material transferred and accumulated on top of the white dwarf that experiences the explosion, not the rest of the star, which means that basically the ejection of material to the interstellar medium just includes a small fraction of a solar mass, okay? And then, more important than that, the system remains in place, which means that novae are recurrent events. They can undergo a second explosion after quite some time, a third, a fourth, and actually something like 100,000 cycles, Okay, and okay, so how often can we, like, again, put a PhD student, now that you have like very young people here, maybe some of them thinking about doing a thesis, okay, in the future, can we propose somebody to observe, you know, like 2 consecutive nova explosions? Well, in general, it's not a good idea. Okay, why? Because the time you need to wait for the next explosion is something between 10 to the 4 and 10 to the 5 years, which is a little bit more than the typical duration of a PhD. Okay, just a little bit more. Okay. However, there is a class here, you see, there is a class of objects that explode much more frequently, okay? And they correspond to what I put here on the next slide, recurrent novae, okay? That explode, you see, we have observed them in outbursts repeatedly and in the typical range of time between 1 and 100 years, okay? The record holder is in the Andromeda galaxy. We have observed that, and explodes every year. Actually, with the people in the collaboration that we discovered that object, we bet about when is going to be the next one. August 13, August 15. I don't know why they always explode in holidays, okay? Anyway, so just to ruin our life, basically, right? But anyway, I'm very bad about gambling, so I always lose, okay? I never catch. But anyway, every year, plus minus a few days, they are exploding. By definition, this class is called recurrent novae and implies the evidence for more than one explosion. Okay, we only know like basically 11 in our galaxy, recurrent novae, and that's again another funny moment because all novae are recurrent, I told you, but not all novae are recurrent novae. Okay, so we call recurrent novae just these 11 ones that have been positively observed in outbursts more than once. Even we suspect that all of them are recurrent, right? If I would have the power to rename, I would change the name because this is really confusing, right? But again, it's the inheritance that we get from a previous generation of people that were not maybe very careful or very good, I mean, very good scientists, but not very good linguistics or whatever in naming these things. Okay, the important thing is that in this recurrent novae, only these 11 of hundreds, actually thousands of nova explosions that we have observed, we believe that the white dwarf grows in mass. And that's interesting because if the white dwarf grows in mass, at some point it will reach the Chandrasekhar value and it may destabilize and explode as a type 1a supernova. Okay, and so that's like one possible path that could explain the origin of this supernova explosion. I don't know whether you have been reading the news, but there is a very famous star called T Corona Borealis, okay? It has been in most of the newspapers. This is a recurrent nova, one of the 11 in our galaxy that explodes every 80 years, okay? So we have observed that, you know, in different centuries, and this explodes every 80 years. And guess what? The next explosion is expected to happen in 2025. Okay, so that's why everybody's rushing, you know, sending papers and so on with predictions about the explosion, nucleosynthesis, and so on. But again, let me tell you something that I discovered just a week before. I was giving another seminar, and then I ended up finding this paper. When the next T Corona Borealis eruption is going to occur? I said, oh, come on, these guys know. Okay, so let's find out. And then if you read in the abstract, they say it is predicted that the next eruption should appear around March 27. That was last week. So I spent the whole night there, okay, nothing happened. But then, wait, they say you have to read all the abstracts, not just one line, okay? They said March 27 or November 10 or later. I mean, what the hell? I mean, what the hell of a prediction is that, okay? I mean, it's like, please buy lottery, you will win, but you will win today, in 2027 or later. No way, okay? So as you can see, astrophysics has nothing to do with Swiss precision sometimes. Anyway, so nuclear physics information on these nova explosions, okay? As you can see, this is a summary of what happens. The main nuclear path runs close to the valley of instability that is depicted here by these slightly darker squares, okay? And is driven mostly by proton capture reactions, so P gamma, P alpha reactions, and beta decay. So these are the inputs that you need to put in a numerical code to run realistic or at least a feasible nucleosynthesis study of nova nucleosynthesis. Okay, good. So what is the endpoint in the nuclear activity? Well, it's calcium, not because I finished the figure there. Okay, it's simply because I have run networks up to iron or something. Above calcium, there's nothing happening. And actually, we can verify that by comparing with observations, okay? So remember that in a nova system, neither the white dwarf nor the binary system get disrupted by the explosion. That means that you can, after the explosion, go there, look, determine composition, and so you know exactly which elements have been produced, okay? And we have done that for hundreds of explosions. So we have some idea that basically nothing anomalous occurs above calcium, okay? So in essence, no heavy metals are produced. Yeah, no heavy metals are produced in a nova explosion, okay? And then again, you can neglect neutron captures, alpha captures. They do not play a role in this scenario. They are relevant in other environments, for instance, in type 1a supernovae, okay? But not here. Good. Except that some years ago I was intrigued. I mean, time flies. When you see these type of things, I mean, I did that 20 years ago. I mean, anyway, so it's better not to think about it. So I was wondering, okay, a nova explosion occurs when you are transferring material from a star into the white dwarf. The usual assumption done until then was that the companion stars basically have a solar composition. They are similar to our sun, okay? But what if they are not? Okay? In our galaxy, we know there are stars that are called metal deficient. Okay? They don't have, essentially they are 99.9% made out of hydrogen and helium, nothing else. Okay? We know them. The record holder is an object that has a metallicity, so everything that is not hydrogen and helium, another wonderful name that we use in astrophysics, metals. Okay? So lithium, we call it a metal, okay? And a noble gas, we call it a metal as well, okay? Anyway, so anything that is not hydrogen and helium in astrophysics is called a metal, okay? And then we have recorded metallicities 10 million times smaller than in the sun. That's the record holder in our galaxy, okay? Which means 99.9999999% is hydrogen and helium, okay? Fine. So what happens? These objects exist. We have observed them, okay? So what happens if you form a binary system and the companion is one of these metal poor stars like those we have in the halo of our galaxy? Okay, well, maybe the nova explosion that will occur will have different signatures, okay? So that's what I explored in that paper, 2007, and I could see an extension of the nuclear activity above calcium, actually reaching copper or something like that, okay? So this is something you see here, compare what is the extent of the nuclear activity up to calcium in a classical novae with the case of a nova occurring in a very metal-poor environment, and as you can see, there is some activity going much beyond that, up to copper, as I said, and this is essentially driven by some sort of a weak RP process, okay? So basically a succession of rapid proton captures. And this is a paper that we did in collaboration with the North Carolina group that is going to be submitted tomorrow, and this is, or later, maybe, no. He said, I mean, Thanasis promised me tomorrow is going to be submitted. I hope that, okay? Theoreticians are more honest in that sense, okay? Anyway, so that's what he said at least. Anyway, so now things that you can find in the ejecta. Let me see how, okay, how much time do I 10 minutes? Okay. Well, whenever you are tired, just tell me and then I stop, okay? No problem. Anyway, so something that is interesting, that is one of these predictions, has not been seen yet. So we are putting our cards up here, is the presence of radioactive elements in the ejecta from a nova explosion, okay? There are several. The most strong signal, and again, I can elaborate on that long. The most strong signature is a 511 kV line. Okay, from your basic training in in quantum physics, probably you remember 511 kV is the typical signatures when you have a positron and an electron that annihilate. You power two photons at 511, which is the rest mass of an electron. And I mean, rest mass energy of an electron, right? So these basically we have elements like fluorine 18, the same one, by the way, if you ever like feel bad, and people suspect you may have a tumor, and instead of just opening and see whether your tumor is there or not, you can experience something called a positron emission tomography, a PET, which essentially works with the same isotope that is believed to be produced in nova explosions, okay? So you ingest something that contains fluorine-18. Fluorine-18 decays in your body, releasing positrons that annihilate with the surrounding electrons of the atoms that you have there and generate gamma rays, okay? You can monitor that and see whether these gamma rays come from a region, basically a part of your body in which there is a high metabolic consumption rate, okay, or not. And if it doesn't come from the right place, then you are in trouble, okay? But let's hope that nobody needs that in your life. Anyway, 511, and then there are specific signatures due to the disintegration of some elements, sodium-22 at 1275 keV, beryllium-7 at 478 keV. So these are specific signatures of the elements that you are there. That would be a wonderful diagnosis for nova models. Unfortunately, remember, supernovae, for the first time, observed in 2014. Actually, that was the explosion. The analysis was later, so it was about the late 2010s. Okay, that was a prediction made in the 70s. Okay, so it took 40 years to verify. Novae that just eject a small amount of material, not the whole star, like in a Type 1a supernova. Well, the detectability of this signature is so small that you really need an explosion occurring in Palermo. Okay, just next door there. Okay. Anyway, but again, we hope that this will be an observable that we will be able to watch and verify one day. Again, up to now, all what we have managed to do, this is a work that we did in collaboration with Roland Dill and his team. We have just obtained upper limits, okay? We don't detect the gamma rays. That means that the maximum amount of beryllium or sodium present in the ejecta must be that. And then you can compare with the values that you get in your models and see whether they agree with estimates or not. And up to now, we are not in conflict. So we agree with the upper limits that have been obtained. Good. Finally, on this part, recall that all these are numbers coming up from a computer. So you have to have the best input physics possible to be able to provide reliable estimates. And this is a wonderful story that has a span for more than 20 years. In an effort led by Christian Eliadis in North Carolina, we published a list of reactions whose uncertainty affects predictions of a nova nucleosynthesis, okay? And again, if you imagine you go to the European Space Agency and where they have some wonderful objects flying around with telescopes, and then you say, oh, can you repoint your instrument to observe a nova explosion somewhere? We have an error bar like this, okay, but who cares, right? No, I mean, they will not give you any credit, right? So reducing the uncertainty in some nuclear reaction rates make you more solid or robust predictions, okay? And the funny things, and I'm extremely grateful to the nuclear physics community, is that most of the nuclear reactions that were identified in this study have been actually improved to the extent that there are only 3 reactions basically uncertain enough in the field of nucleosynthesis in novae, okay? That's totally at odds with what happens in most of the astrophysical scenarios that we have around, where the list of reactions that require some improvement is very, very large. Okay, well, still, even these are the big 3 in the framework of nova explosions. There is some progress. This is a work that we did with a group in Ganil that was published in Nature Communications that helped to constrain one of the rates that has to do with the destruction of sodium-22, and then we have obtained more reliable estimates of the detectability distance to a nova explosion, for which this signature associated with sodium-22 decay can be detected, for instance. Okay? Good. Again, as I said, all these are numbers coming up from a computer. How can you be sure? Well, there are different things that you can think about it. This is one. Okay. Well, you can hire, now that Elon Musk wants to go to Mars, maybe we can get in touch and get like a spaceship and go and observe in situ one of these explosions. I wouldn't do that, okay? That's risk, that's really risk. I mean, going to Mars is really a dead mission, but going near, a binary system in explosion. Again, I can tell you a few things that are absolutely wrong in this photogram from Star Trek, but I don't have the time to do it. If somebody is curious, ask me later on. But then there are better ways to do that and constrain our models, okay? One is simply take a spectra from your sofa at home, okay, using a robotic telescope, okay? Then you infer the abundances, and then you can compare with the theoretical predictions, okay? You can see that the fit sometimes is quite good, okay? Problem is that usually what you get from the spectra, in many cases, are elemental abundances. So you get, for instance, the overall amount of oxygen present there, but you cannot distinguish which part is oxygen 16, 17, or 18, okay? So in recent days, in recent times, we have something called high-resolution near-infrared spectroscopy that allows you to obtain isotopic information for some elements, but not for all. So depending on which, wavelengths these transitions occur, okay? But still, we are far from there, and basically what we get are elemental abundance. But if you really like isotopic abundances, there is something, some of you know, others probably not. Our solar system, we have explored different places in the solar system. We have retrieved rocks from the moon. We have taken samples from Mars, from different asteroids, and so on. Essentially, they exhibit a large variation in elemental abundances, okay? So that's why, for instance, the surface of Mars is red, okay? Because of the presence of iron oxide in larger amounts than what we have on Earth, okay? But when you compare the isotopic ratios, so how much, for instance, carbon-12 over carbon-13 you have in a terrestrial rock or in a on a Martian rock, the agreement is incredibly astonishing, okay? So the solar system is quite homogeneous isotopically, even it is not in elemental abundances, okay? And thanks to that, in the 80s, last century, people started to realize that when examining primitive meteorites that were retrieved from the surface of our planet, they were capable of extracting very resistant spherules of just a few microns in size that when analyzed in a mass spectrometer, they reveal anomalies in isotopic proportions like nothing else, by orders of magnitude larger than any other sample retrieved from the solar system. They coined them pre-solar grains because they think that these little spherules are the result of condensation of material ejected by a star at the end of its life, okay? And shortly before the formation of the solar system itself. So they were incorporated into the nebula that gave rise to the solar system and the formation of the planets, okay? And then depending on the properties they have been attributed, comparing again models and properties of these grains with different objects. The main contributors are intermediate mass stars, what is called AGB stars, okay, that essentially experience some mass loss, okay, during their life, and we believe that they have clear signatures of the activity produced in that type of stars. But at the turn of the century, by 2001, a group in St. Louis actually wrote me and they say, oh, we have found some grains that may look like your predictions for NOVA models because they have nothing to do with the typical families of grains there. And they are anomalously enriched in nitrogen-15 and carbon-13. These are the main fingerprints of NOVA explosions, and even some in silicon-30. Okay? These are signatures that are basically mostly produced in NOVA explosions. So maybe some of these grains were the first ones that actually have been obtained, isolated on Earth from primitive meteorites that reflect an origin that points towards NOVA explosions, okay? Since then, we have identified other grains that could be pre-solar NOVA candidates in the current inventory of pre-solar grains. And something I don't have time to explain is that for the first time, we managed to isolate a grain that technically could not exist, okay? So it essentially violates what was believed until 2019, that was the co-condensation of an oxide-rich phase with a carbon-rich phase in the same grain, okay? If somebody is curious about it, just ask me later. That was published in Nature Astronomy. Okay, just to finish, again, if I have like 5 minutes? 5 minutes. Good. Most of our knowledge on the physics of these nova explosions rely on models of spherical symmetry, okay? Meaning that we get information at different depths, but we think that everything at different angles, it has not angular dependence in essence, okay? Which is like a good approximation. If you look at the sun, it looks like a spherical, okay? So again, starting with the spherical symmetry is something that, okay, while we don't have anything better, that's okay. But of course, there are things that we cannot do in a spherical symmetry in one dimension. For instance, we cannot investigate how ignition occurs and how the flame, this front, propagates through the star. Or for instance, what happens in the long-term evolution. I mean, remember that you have two stars, a white dwarf and a companion. The white dwarf at the outer layers is the one that explodes. This material gets ejected, will collide with the disk of material that surrounds the white dwarf, and maybe a fraction will impact the companion star. How this is going to affect the next nova cycle, okay? I found that this was a very interesting question, and when I have a very good idea, I put somebody to do it. Okay, so I hired a smart PhD student. I said, why don't you investigate the long-term evolution and see what happens? And she did, okay? And actually, what she modeled was what happens when the ejector here in green impacts the disk. These are three-dimensional simulations, a slice from above and a slice from the side. And what is the level of contamination on the companion star, okay? And this is basically what she explored, different simulations, and you can see how material impinges the outer layer of the companion star, and since novae are recurrent, this may affect the properties of the next explosion, okay? Well, we did that in 3D, not earth-shaking resolution, I would say. That's why I put another PhD student to do that in 2D in axisymmetric simulation. And you can see now the level of resolution, even the quality of the movie that I'm showing here is not good, okay? You can see the formation of hydrodynamic instabilities as the ejected material essentially sweeping the whole disk, creating even a cavity that for the first time has been claimed to occur there, and that could be tested probably using polarimetric observations. That is something fashionable these days in astrophysics, okay? Good, what else? Yeah, there has been a mystery regarding nova simulations that has been intriguing everybody. That is the fact that when you have a white dwarf and a solar composition material, okay, and this material accumulates on top of the white dwarf and then experiences an explosion, we take a spectra of this ejected shell, and what we see is its metallicity is not solar. It's not 2% in metals. It's something like 20%, 30%, something like that. Where are these source of metals coming from? And there have been suggestions and mechanisms based on spherical symmetry that didn't work. The best approach for that was that guided us was a work done in Israel where they actually exploited what happens when you move from 1D to 2 dimensions and allow the material extra degrees of freedom, okay? And as you can see, you form these sort of convective eddies that are capable of crossing the outer layers of the white dwarf and essentially dredging up material. This was refuted by the group in Max Planck. So I said, wow, that's great. Let's see what we can do in the Mediterranean, okay? And whether we obtain a third different result or something that corroborates that. So again, I put a PhD student. This is the examples of the same instabilities that we observe in the clouds when a cloud is moving with some velocity with respect to the surrounding air. And as you can see, you form these sort of vortices here that are basically the early stages of this mixing between cloud material and the atmosphere. So we know that these instabilities occur. Okay, well, we tested that in 3D. I just show you a glimpse on the simulation that we did. And maybe you can see that by just moving to 1D to 3D, we can actually pump up material from the outer layers. This is not artificially, there is not somebody here pumping things, okay? It's just moving from 1D to 3D, allowing extra degrees of freedom. And basically, as you can see, we are polluting the outer layers of the white dwarf with material from the, we are polluting the accreted envelope by material from the outer layers of the white dwarf, and most interestingly, at levels that agree with observations, okay? So that was a paper that we published in Nature some years ago, because again, we have obtained not only the mechanism that works in 3D, but also the levels that are being reproduced and observed in those nova explosions. Okay, last thing is the X-ray burst. Okay, I don't have time to cover that. I suspected that I would run out of time at this stage. So I just want to draw your attention at the last slide here. Okay, remember we have a neutron star, and ejecting material from a neutron star has a problem. The escape velocity from a neutron star is much larger. It's about 2/3 the speed of light. Okay, so again, people for many years have discarded the possibility that during an explosion on the surface of a neutron star, we can eject something, except that I hired this guy, Thiago Herrera, and I asked him, okay, can you test what happens when you have a very luminous explosion? In a very luminous explosion, there is a lot of radiation pressure. This radiation pressure can push material, okay? And actually, by building a model of a wind, okay, that is pushed by radiation together with hydro models, for the first time, we have quantified the possibility that X-ray bursts essentially lead to the ejection of material from the surface of a neutron star. And again, I don't want to abuse your generosity, and I think that would be like a good time to thank you for your attention. Please. Me too. Yeah, okay. Sure. Let me elaborate that. So in a nova explosion, in a typical nova that we observe in our galaxy, for instance, we have some idea to infer the rate at which material is actually being transferred, okay? Typical values are of the order of 10 to the minus 10, 10 to the minus 8 solar masses per year. These are the values that are essentially inferred from observations. Now, if you run a model with those values, you get periodicities of 10 to the 4, 10 to the 5 years. That's the first thing. So that's where this number is coming from, because obviously nobody, even the Chinese years ago, were observing a nova 10 to the 5 years ago. Okay, no way. So these are just purely speculative, but again, there is some agreement in the community that these numbers, based on the inference of mass transfer rates, are the right ones. Now, why some objects experience an explosion every year? Well, again, models try to help that, and basically what we have obtained is that in order to obtain such a short recurrence time, you have to go to extremes. You have to consider that the white dwarf is actually very, very massive, close to the Chandrasekhar value. The mass accretion rate has to be larger than that, and the object has to be very luminous. If you do that, you can obtain in the computer an explosion every year, actually even shorter than that. But again, obviously, what makes this recurrent novae so unique is that to have all these combination of parameters together is complicated. It's not the usual case. So that's why they are so rare in nature, essentially. And then something related to your question is what happens in between. So are there explosions at 10 to the 3 every 1,000 years? So is there a continuous sequence here, or there is a gap in between? And this is, again, one of these million-dollar questions that we don't know. Actually, depending on, I mean, I asked, obviously, to all my expert colleagues that are, work on the observational side. Some claim that, yes, they suspect that there should be a continuous distribution. Others claim that the conditions that lead to the 1,000 recurrence times are not inferred from nature, so probably there is a gap. So it's an open question, okay? Well, we understand the two extremes, but we don't know what happens in between. We need many PhD students, exactly, yes, yes. For 1,000 years in particular. Yeah. More things there.
You talked about supersonic and subsonic propagation of shock waves, for example, during the detonation. But what should be the difference in the results of that between super and subsonic?
So again, the answer is not simple. If you assume that you start the ignition near the center of a white dwarf at a supersonic velocity, simulations tell you that the whole star will be transformed into nickel-56. So you would expect 1.4 solar masses of nickel-56, and this is at odds with observation. So this is ruled out. So we know from the 70s already that a pure detonation, pure supersonic front will not work. Okay. Then people said, okay, if the supersonic regime doesn't work, let's try a subsonic. It was working better, but still there were some elements that were not nicely overproduced. And again, what we do is compare with the spectra distribution of elements at different depths and see whether models agree or not with this, pattern. Now, what is the situation? Something I didn't mention here. What is the most accepted situation? A combination of both, as usual, okay? So the models that are more reliable in terms of matching the observables are those that begin with a deflagration, so subsonic front, and at some density experience a transition into a supersonic regime and then complete the business, okay? But again, yes. But again, why this is happening is now the big question. Nobody knows really by first principles what is the region of this transition between a subsonic and a supersonic regime at the densities that are required to match the observables. Okay, but that's all what I don't work specifically on that area, so there is no more than this that I can tell you, but that's the latest. So people are struggling to get the best models as possible that matches everything. There's still room for improvement. Aurora had a question.
Thank you very much. Always a pleasure. It's amazing. So what is let's say, it might happen that these two binary, so these two systems somehow, if we speak about a white dwarf, so they can merge. So and maybe it can happen also in this kind of scenario that you lose some contribution because of the merging. So how can you, let's say, estimate? Verify or estimate.
Good question. I remember when I was younger, I have been younger. When I was younger and actually a student and an undergraduate student, I remember my teacher of astrophysics was an expert on supernovae. Okay, and so the canonical view by then, okay, was that all type 1a supernovae are identical. So there is a single path to get that. That's why all the explosions look like similar. Okay, I was wondering, okay, fine, but if there is the chance to obtain an explosion by the merger of two white dwarfs or a white dwarf accreting material from a normal star, how to prevent that? Okay, I always thought that there should be more than one path to lead to the explosion because, again, one is more difficult than another, but I was thinking, fine, but tell me a reason that really proves that this is impossible, and that doesn't exist. Okay, now what is the situation? 70% of the supernovae are identical, 30% are not. They have anomalous properties. So maybe this is telling you there is more than one path, and so the explosions are similar but not really identical, and that's the reason for this diversity in type 1a supernovae. Okay, so that maybe it's one possibility. Second, you may think, okay, why don't we do like with kilonovae? We can observe gravitational waves in the merger of two neutron stars. Can we do that with white dwarfs? The answer is yes and not. Okay, in principle, yes. But the problem is that the frequencies at which the gravitational waves will be emitted, according to the experts, will be identical to the frequencies generated in terrestrial earthquakes. So you cannot distinguish the signal from an earthquake that has occurred like in Myanmar recently, right? So the only possibility, so they contribute to the background noise in gravitational waves, but to detect them, you have to go to space, and in an environment free of these frequencies, okay, you will be able, and that's the plan for the LISA mission that in principle is planned for something like 2035, okay, when I will be retired, basically, okay? So that's basically the idea. So yes, in principle, we'll be able to, I mean, remember that the kilonova explosion is the first direct evidence, if you can call it direct, of the existence of the merger of two neutron stars. That has been speculated for many years, but that's the only proof of evidence that this actually is happening. Okay, we wait for a similar, phenomenon in the regime of white dwarfs. They have to be more frequent because there are many more white dwarfs than neutron stars. So there are statistics already claiming how often a signal like that could be detectable from space. Okay, so much more often than in the case of two neutron stars.
Question coming back to this lithium. Yeah. So somehow, yeah, this is kind of a new source of lithium production. Is that, new? Because I've never heard about it.
Let me be honest, that is always what I like to be. These head-on or even off-center collisions are very rare. Okay, so I'm not claiming that this is the site where lithium is made. All what I said is that this just proves that wherever a system containing hydrogen, and because in this case a collision, this hydrogen is heated to temperatures between 10 to the 6, 10 to the 7 Kelvin, you will produce lithium. So what means is that probably there are multiple things contributing to the origin of lithium. There is some percentage in the Big Bang, novae for sure. There are others, but again, like some people have been claiming lately in the last 2-3 years, all lithium-7 is made in novae. I don't believe that, okay? That's the message. Giuseppe.
Thank you. So I have two questions. First one, you showed us a table with a list of elements involved in the process of supernova and nova, I don't remember.
Okay.
Is there any elements that we should study in a better way from a nuclear physics point of view in terms of nuclear reaction? And
question. So I was showing you the uncertainties related to novae simply because even if I restricted the number of slides, I ran out of time, as usual, okay? But anyway, so for novae, the problem, in my humble opinion, is no longer a nuclear physics problem. So there are other more intriguing aspects that we don't know in the modeling, mixing, rotation, whatever. For nuclear physics, we need to improve a few things that will give us better information, a better insight. But I think that most of the nuclear physics inputs that we require for nova nucleosynthesis are basically well determined. But this is not the case for other. And so here I had some extra slides. For instance, type 1a supernovae. This is the list of reactions that need to be improved for type 1a supernovae to have like a good picture of the nucleosynthesis that is produced. What about others like X-ray bursts? I think I have it somewhere, sorry. Here. Too fast. Yeah. Yeah. Come on. This is not my usual pointer, and so I have some here. Yes, so these are the list of reactions, not only whose uncertainty changes the nucleosynthesis, but also changes the energy generation rate. So they alter properties like the shape of the light curve and everything. As you can see, the list of reactions is huge. What is the problem? Well, most of them rely on short-lived radioactive species. So when I approach the nuclear physicists, they say, well, this is impossible to be measured directly, at least. We can maybe think about some indirect methods to infer that, maybe Trojan horse or some other techniques that are, excel here in Catania. I don't know. But again, there are studies like that that actually suggest a large number of reactions that are really unknown. And again, we would benefit dramatically by getting a better insight. Most of them are based on Hauser-Feshbach theoretical estimates. There is little spectroscopic information, and then the uncertainty is, large, quite large.
Second question is there any beer test, supernova beer test after this seminar?
I would love it. I would love it.
Very curious about it.
Okay. That's a good idea, good suggestion. Ah, the Star Trek, yeah. Usually I put that when I teach a course for a summer school. I have more time, and then I go to this. Let's see what I can do that quickly here. Sorry, just one moment. Yeah, here. Okay. So I remember watching, I'm a big fan of science fiction, in particular Star Trek. So I have seen all the episodes. And so I was puzzled to see there was this episode in which an astrophysicist is sent in the Enterprise to observe an X-ray burst explosion. So I said, no way. I mean, they cannot do that to me. So I was watching with interest. And it's funny because they said 3, 2, 1, now. And then the star blows up. And I said, I mean, not later. This one was at the second. I mean, come on, astrophysics doesn't work like that. Even recurrent novae that are quite like clocks, they exhibit some, I mean, they don't work to the second, okay? But fine. Anyway, the important thing here is the following. They, as the astrophysicist in the movie tells, with whom I would like to have some words, okay? They said, well, this is a red giant, and this is the neutron star. It's actually stripping material, fine with that. This is red, as you can see. But what happens with this material? This material keeps on being red all the way. I mean, a red giant is red because of simple quantum physics, like Planck's law tells you that what is the maximum emission at a given temperature. Okay, but when the object actually gets ejected and gets exposed to the 3 Kelvin that we have in the universe, okay, the temperature will essentially drop and it would be invisible in the optical, okay? It will emit, I don't know, in the microwaves or something, but not in the optical, so it will not be red. This is like somebody's painting in red the material, and of course it makes a very nice visual thing, but again, it's a big mistake in basic quantum physics argument, right? Well, I mean, usually, yeah, they don't give a damn about these things, but it's good to test when you have physics students, like, okay, what do you see here? Is anything anomalous? Do you think it would be in reality, would be like that? It's like a wonderful, I mean, that generates more discussions than a usual typical boring problem with, an integral with a Planck law and everything. Yeah, hard to say. I mean, a neutron star, yeah. I mean, we can work it out and see what would be, but probably would not be blue. This is just to contrast, okay? Since I'm from Barcelona, the color of my football team are red and blue. I'm happy with that. But in any case, yeah, I think that doesn't work. That doesn't work. Any other thing? Curiosity? Please.
Metal poor stars, when
Yes.
their creation is made of metal poor, actually you reach higher masses than with
You mean, yeah, okay, I understand your question. Yeah, I understand your question. So you okay.
reach higher masses.
Sure. Okay, so this is a big topic, again, something that we don't know, because again, people remember that if you read something about the first stars that were generated in the universe, what we call population 3, this is like with all people, like third age, right? And so on. Population 3, the first that appear immediately, some million years after the Big Bang and so on, there is no single evidence of just one of these population 3 stars discovered, okay? They are theorized to exist. They have not been discovered. There is one that is called the Methuselah, the biblical character, right? Star that people claim that is one, probably the oldest and so on, but again, there are big error bars. So people speculate that because of these stars were formed with purely Big Bang material with basically nothing else than hydrogen and helium, just traces of lithium and nothing else, you could form actually larger objects, like having 300 solar masses, 400 solar masses, things like this, okay? Good, so this goes with the massive thing. But again, this was for the population 3, okay? But there are studies that suggest that, yeah, that's true. You could favor the formation of very massive stars, but there are people that claim that this distribution, when you compare the number of stars that you can form with population 3 objects, okay, they have like a double peak distribution, okay? There are others peaking at about 8, 9, 10 solar masses, so at a small range. So it is possible to form a binary containing an object that will evolve into a white dwarf as well, okay? So that's why I picked up that message saying, fine, if you can, okay, you can form very massive stars that will experience a supernova explosion, essentially. But you can form also objects that are metal poor of lower mass. You can form a binary system containing one of these metal deficient stars, and then actually evolve into some sort of a nova with a metal poor companion, okay? And that was the origin of this work. I hope that that explains.
Another question?
I think I have exhausted everybody.
Yeah. Okay, if not, let me thank again Jordi. Have a good afternoon.